Hi, so this is my fourth video on electromagnetism. So in our last video we talked about electric flux, and in this video I want to talk about Gauss's law. So in the last video we learned that the electric flux through a surface with the charge inside is equal to the integral over the whole surface of E dot dA. And E is the electric field vector at a point on the sphere. And dA is the area vector in a little area element dA. And the integral of E dot dA is equal to the electric flux phi, the integral over the whole surface. So that's what we did in the last video. And now I want to talk about Gauss's law. So Gauss's law says that if you have a closed surface, and let's say it has a charge inside, so this surface has a charge inside, and it's a closed surface, so there's no openings, then if we take a little rectangle dA, and here's the electric field vector at that point, then it says that the flux is equal to the integral over the whole surface of E dot dA, and that's equal to the sum of all the charges inside. So the sum of all the charges inside divided by epsilon naught. So this is the sum symbol. So we're adding up all the charges inside and dividing them by epsilon naught. So Gauss's law says that the electric flux through a closed surface is the sum of the charges inside divided by epsilon naught. So that's what Gauss's law says. And remember, this is only for surfaces that are closed. So if we have a closed surface, then we add up all the charges inside it and integrate over the whole surface. So we add up all the charges inside and divide it by epsilon naught to find the electric flux through the closed surface. So let me do an example using this. So let's say that we have a sphere, but it only has a charge on the outside covering of it. So only the surface of the sphere has a uniformly distributed charge. So the surface of the sphere has a uniformly distributed charge. So now let's talk about finding the electric flux a distance literal r inside the sphere. So there's a smaller sphere inside this larger black sphere with the radius little r. So we want to find the electric field there. Now we don't want to find the electric flux there, we want to find the electric field there. So we can use Gauss's law to solve for the electric field. So over here is Gauss's law, we can use it to solve for the electric field. So we want to do that for a radius little r inside the black sphere, and a radius little r which is bigger than the radius of the black sphere. Okay? So I'm going to erase Gauss's law now, so you should probably write it down if you want to. Just remember that all it says is the surface integral of E dot dA is equal to the sum of the charges inside the closed surface divided by epsilon naught. So I'm going to erase this now. You can rewind if you want to write it down. So let's start with the with the sphere that's smaller than the radius of the big black sphere. So we want to find the electric field at any point on this sphere. Okay? on this red sphere. So we use Gauss's law. So Gauss's law for little r, for this sphere, this little red sphere, says that the integral of the electric field dot dA is equal to the sum of the charges inside the sphere, the red sphere, divided by epsilon naught. Well, let's look at the charges inside this red sphere. Inside this red sphere, there's no charges, so the sum of the charges inside is 0. So that means this equals 0. Now, let's do the left-hand side. So we can, since the electric field over here, that's what we want to solve for. So we want to solve for the electric field. So what we're going to do is factor out the electric field. So we have E times the integral of dA equals 0. Well, the integral of the area can't equal 0 because this sphere has to have an area because it has a radius r. So it must have an area, so this cannot equal 0. So that means the electric field must equal 0. Because the integral of E dot dA, the dA can't be 0, so that means the electric field has to be 0. So we have the electric field equals 0. So the electric field on a sphere that's smaller than this big black sphere, so any red sphere that has a radius that's smaller than the black sphere, the electric field is 0. So anywhere inside this black sphere, the electric field is 0. So now we want to find the electric field outside the black sphere. So if we have a sphere with radius r outside the black sphere, using Gauss's law, we have that the integral of E dot dA over the whole surface is equal to the sum of the charges inside. Well, the charge inside a sphere with the radius bigger than the black sphere would just be Q. Because remember, the black sphere has a charge Q on it, a uniformly distributed charge Q, divided by epsilon naught. And then if we simplify this, we have E times the integral of dA equals Q over epsilon naught. The integral of dA is just the area of this bigger sphere with radius little r. So E times 4 pi r squared equals Q over epsilon naught. And then we solve for E. We have E equals Q over 4 pi epsilon naught r squared. So that's the electric field outside this sphere. So the electric field outside the sphere, the black sphere, is E equals Q over 4 pi epsilon naught r squared. Remember, Q is the uniformly distributed charge on the surface of the black sphere. So now we have the electric field inside equals 0, and the electric field outside equals Q over 4 pi epsilon naught r squared. So now, after that, that's an example using Gauss's law. I want to rewrite Gauss's law. So Gauss's law says that if you have a closed surface, so there's no openings, and there's a charge inside, and we have a small area element dA. This is the normal vector to that element, and it has a magnitude which is equal to the area of that element. And here's the electric field going through that element. So it's E. Then Gauss's law says that if you have a closed surface with a charge Q inside, that the surface integral over the surface of the E vector dotted with the dA vector equals the charge inside the closed surface divided by epsilon naught. So that's Gauss's law, and then you just plug in your values and you can use it to solve for the electric field, and this is also equal to the flux. So that's Gauss's law, and I did an example of it in this video, and in the next video we're going to do one more example of it. Hope you like this video.